I'm here with Bob Blainey, who was the creator of a language called Dash, which is now Gazprea, that we built the compiler for in 415. Bob is now at a vice president position at RBC for the last 3+ years, but Bob was for 15 years at IBM where Gazprea was created. So Bob, from your recollections, what was your main motivation to start the idea of that language that was Dash at the time and then became Gazprea?
Yeah. Well, so just for context, we were a group at IBM that was focused on hardware acceleration of various sorts, various types of workloads. So meaning GPUs, FPGAs, different types of memories, et cetera. And so that was our main mission as a group. And one of the teams that we worked with did some work with financial modeling. So we had a group that did financial risk analysis in particular. And so it was a very challenging workload to accelerate. And we were trying many different things, GPUs, FPGAs, clusters, a lot of different things. And one of the challenges we encountered along the way is, how do we actually get the code to be written in a way that can exploit all these different, various types of hardware acceleration that we thought would play well. And it was written in C++, most of the code. So how do we go from that C++ world to a world where it can exploit all this hardware? And so we actually tried a lot of different things. And one of those things we tried was to create a new higher level programming language that could automatically parallelize down to these different hardware targets.
Yeah, I remember those times. And so that is one of the reasons for the focus on numerics in the language, right? The use of generators, the use of representation of arrays and tuples and all that, because it came from that application environment. But the language also has a bent that I like to comment on, that is a language developed by a compiler designer. Someone that understands compilers very well. Can you speak a little bit about some of the thinking going into the language to make it so that it can actually be, naturally parallel and can be more easily optimized in comparison with other similar languages?
Yeah, for sure. Yeah, so I mean, we had a lot of different kind of inspirations to the language. I would say, like the people that we were targeting, that is the mathematical modelers, the people that were kind of coming up with the risk models and so on. They would use tools like Microsoft Excel, or they would use R, which is good actually. They're very good tools for developing financial models. They're not good tools for putting them into production because you can't get any reasonable performance out of these, or certainly not parallelization. So that one of the motivations was we want to be able to give the modelers a similar kind of experience. They should be able to model in mathematical language, but we have to be able to get that to compile, down into something that's efficiently parallel. So, I mean, the other motivation I would say we had was really going all the way back to data parallel language like APL, where you encapsulate data parallelism very efficiently in the expressions of the language. And it gives the compiler a lot of information to be able to generate good code. So a good example of a change between something like R and Dash is really adhering to static typing, where, we otherwise would have been left with the difficulty of having a runtime compiler if it was a dynamically typed language. But by choosing static typing, with a certain amount of type inference and so on in the language specification for convenience, but nevertheless static typing, we're able to, infer what we need to infer at compile time and then, generate very good code. And because a lot of the operators are implicitly data parallel, like matrix or vector operations and so on, those things are, I won't say easy necessarily to parallelize, but the parallelism is apparent. There's nothing required of the programmer to further identify the opportunity for parallelism. And so those are the types of constructs that we zoomed in on language, because if we had not done that, either we would have been unable to parallelize at compile time, or we would have put a lot more burden back on the programmer, which would have put us right back where we started, with something like C++.
So I know from your history, from having worked with some of your code when I was consulting with IBM, and from all our discussions over the years about your experience with pointer analysis and all the work that goes into pointer analysis for language like C and C++. Was that also a concern or a consideration when designing Gazprea?
It was, yeah. I mean, any type of aliasing that you have apparent in a language, whether that's caused by pointing to references or it's caused by function calls, any of this type of aliasing can be a major barrier to doing any kinds of optimization, certainly parallelization. So it was definitely, so one of the things that we tried to focus on was creating the opportunity, at least for pure functional programming within Dash. And so that when you're actually doing operations on a matrix, you can do that using a function that has known not to have side effects, on its parameters, for example. That's an example. We discourage the use of pointers by and large, and I'd say one of our inspirations there was at the time the language Rust was just getting started, but they had come up with some really good ideas of how to sort of maximize the use of stack allocation over heap allocation. And it discouraged the use of sort of arbitrary use of pointers, which is, again, it's generally a good thing. And there's often no need to have sort of general purpose pointers or heap allocated storage. You can have storage passed up and down the call chain effectively using, again, I think we were quite inspired by the ownership rules in Rust. And I think that's something that we tried to take into the language as well.
Okay, so the other aspect of the language was a concern about dynamic memory allocations versus the malloc versus free in C, and there are some innovations in that area too, right? To enable the system to manage memory, but without resorting to garbage collectors and such.
Right. Right. Yeah. That's yeah. Again, I think if you see languages like Rust and Swift, they kind of went in a similar direction, which is to say, dynamic allocation is allowed, and it use something like reference counted garbage collection to keep it simple. But in fact, most of what you need to do, you can do using stack-based allocations, right? And that doesn't mean allocating on the stack frame. It just means that allocations and frees can sort of follow a call return cadence rather than having some other arbitrary lifetime. Because the biggest problem with dynamic allocation is sort of the arbitrary lifetimes of objects, right? Where it's hard to track where they come alive and where they die and where they transfer ownership. If you can make that explicit at call return boundaries, you can simplify a lot, and you can limit the amount of storage that needs to be garbage collected, which is always a challenge for sure.
Yeah, that's a very interesting aspect of the language. So two more questions before I let you go. One is, students will be curious as to why the language never got out to the public, right? And I know the story, but I would like to chat with you a little bit. I remember this Extreme Blue project and such that some of our own students participate on. So a little bit of that story, and that might be helpful for the students to understand the process in a corporation of making something go out the doors, right? So,
yeah, for sure. Yeah, I mean, one thing to know, we did actually complete a lot of the development of the compiler. It was actually generating fairly efficient code, even fairly efficient SMP code. It wasn't quite at the point where it was generating efficient GPU accelerated code. That was something that was still in the works when we had stopped the project, but it was looking very promising. And I think I guess the main lesson to draw away from this is that, being largely complete development doesn't mean largely ready to deliver. And because there's so much more that would need to be done in terms of fit and finish and packaging and support structures and, all of documentation, any number of things that would need to be done to get this properly out the door as a product. And it would, for a company like IBM, it's not just about shipping the software. Once you ship the software, there's a long-term commitment to customers to support it and enhance it and so on. So these are big decisions to be made on the product side. Are we ready to make that type of investment? And in this case, we just weren't. I think in hindsight, we see similar languages have emerged since, like a TensorFlow and so on, that are following similar principles. And so it's regrettable that we didn't ship it as a product, but at the end, and we had to kind of look at the investment case, and it just didn't hold water at the time, and so we didn't follow through.
So it's our benefit to now have a language that we actually have control over. So we have refined the specification site over every time that we do the course. So of course the Universal Format has benefited a lot from you guys allowing us to continue using it. So now changing the topic a little bit, you are no longer a compiler person. right? Now you are vice president in a large organization responsible for IT development in a number of different ways. Um, but I want to bring it back to the students and the experiences that they have in a course like 415, where they take a language specification, they work with Anther, the tool for front-end generation. They target LLVM, that is the intermediate representation for a well-known compiler. So if you can talk a little bit about, from what you know, the skills that they get in such a training and the applicability of these skills, not only to go into a compiler design group, but more generally as a training
Right.
in
Yeah, well, I think if I kind of reflect back on the experience I got, both, as a student studying compilers and then professionally, I think it's like any complex software system. You're going to learn very similar skills. You're going to learn how to reason about fairly complex data structures, complex algorithms, how to bring them together effectively and do integration. It'd be similar if you found somebody in an operating systems course or
Mhm.
distributed systems course. The same types of reasoning are required. And so I think that a lot of that is applicable no matter where you end up, whatever sort of complex software system you ultimately have to manage.
Mhm.
I think the other thing is the social aspects of programming are always going to be portable. The ability to work in a team, the ability to check each other's code, to help each other along in a software project. Those are incredibly valuable no matter where you land. So in the job I have today, I don't do compiler work anymore. I
No,
don't
I-
have that fun anymore. I used to have that fun for a long time. But look, I mean, we build big, complicated software systems, and so it's very similar. I find having the experience of working in code bases that are very large and very challenging to understand and evolve. That's the real world. That's what it's like in most software systems, right? Of any kind of reasonable complexity. So
So I kind of laughing because we did not talk about this before we start this recording. And in the last time that we did this class 2 years ago, I did a post-mortem workshop in the end of the class where basically I got these students to sit in groups that are not their own group and to talk about their experience. And I realized that the main thing that was missing in the class was the social aspects of the programming that, they were there, students had done it organically and naturally, but they were not guided. So
right,
they did not receive the framework in the beginning of the course about, how often they should meet, how often they should check with each other, what code style they would use, that they would do code reviews and things like that. So one of the new things in this fall that I'm very excited about is that we created such a framework, and the students will receive this requirement in the very beginning about the meetings that they have to have, about the making pull requests and having other people review their code, and so all these aspects that you call the social aspects of software development, and it's something that existed before, but it was not structured, and we're going to try to structure much better this fall. So and as you know, this will be our online experience. So my experience in the last few months with online activities is that you do need to have more structure, even more so than when you are able to gather together in a physical
right,
environment.
absolutely. Yeah, it won't happen as naturally, I'm sure. Yeah.
Exactly. So I want to thank you very much for your time. This will be very valuable for the students to get to meet you through this video and meet,
Virtually, anyway. Yeah.
yeah, everything happens virtually these days, and to get to know a little bit more about the creator of the language that they are compiling from. Thank you very much.
No, thank you.